Okay, hi everybody, welcome back. We're going to talk about another method today. We just talked about Newton's method from Isaac Newton. This is called Euler's method, not Euler's method, but Euler's method, as if one who oils something. Euler's method, this is Leonhard Euler. I'm not sure how to pronounce his name. Leonard or Leonard, I'm not really sure. Euler. So, first of all, slope fields. Hey, remember these things? They were good times. A slope field is a way of visually representing a differential equation. If we knew like an initial point, like let's say that I know that I'm going through this point right here, 3, 0, what would the solution look like? Well, you basically just connect the dots here, so it looks something like, I don't know, that maybe. Looks pretty good. That looks like the solution that goes through that point based on the slope field. Okay, cool. It's a good way of approximating a solution. We've seen a few ways of actually calculating solutions. But this is another kind of cool way of approximating a solution to a differential equation, because sometimes these things can get crazy challenging and we might not even be able to solve them. But here's a way that you can approximate it. So get ready. As is typical, you're going to be given a starting point. This is like your initial condition if you have an initial value problem. In the last example, in the slope field that I showed you, it was the point 3, 0, but it could be anywhere. You're given some starting point. What you're going to do, because you have a differential equation, you can calculate the derivative at that point. And so if that derivative is, I don't know, let's say 2, that means that you're going to have a little slope of 2. And you're going to move along that slope of 2 for a little bit. I'm putting that in quotes because you can kind of just define what I mean by a little bit here. It can be 1 unit, it can be half a unit, it could be 20 units. It's whatever you think is a little bit for your given problem. So you basically just move along your tangent line a little bit. You find that the endpoint from that little bit that you've gone, and then you just play the same game from there. You would calculate the new slope at that point, and then just kind of keep following along. You're creating a curve. It's actually not a curve, though. It's more of a polygon. It's a polygonal path. It's just a bunch of straight lines, but it's going to give you a pretty good approximation of what the solution is, visually at least. Let's check this out on Desmos, because why not? Okay, so we've seen this before, slope fields. I've graphed the slope field for the differential equation dy dx, so the derivative, is equal to 2x divided by y. And it looks pretty cool. Imagine that I start at the point 1, 5. Oops. Starting at the point 1, 5 is that green dot there. What I could do, and what I will do, is I'm going to calculate the slope of the tangent line at that point. And I can do this because I know the differential equation. The derivative, the slope, is always 2x divided by y. So if I plug in 1 for x and 5 for y, I know that at this point, the slope is 2/5. And since it goes through the point 1, 5, I get this wonderful equation right here. Y minus 5 equals 2/5 times x minus 1. I'm going to do this just from x equals 1 to x equals 2, so I'm only, my step size, if you will, my little bit, is going to be 1 unit. If I graph this function, I get this nice little purple segment right here, which is, of course, a very good approximation of what's happening to the curve. It's probably a little too long, so you could maybe make it only go from 1 to 1.5 or 1 to 1.1 or something like that. Smaller steps will probably be better for you, but it's fine. Okay, so then I want to find the endpoint of this thing. The endpoint is when x equals 2, so I can just plug 2 into my formula here, and when I did that I got 27/5. I'm going to plot that point. That becomes my new sort of starting point. So, whoops, I keep going down. Cool. So my new point is 2, 27/5, and again I have a differential equation, so I can just plug 2 in for x, 27/5 in for y, and figure out what the slope is at that point. And after some arithmetic, I found that the slope there has to be 20 27ths. And since it goes through this point, I'm using point slope formula again, and I'm getting this equation for the line. And I'm just going to go from x equals 2 to x equals 3. Again, just a length of 1 unit. If I graph this line segment, you see that it's starting to slant up a little bit, and it's still pretty closely following the curve. Okay, so we keep playing this game. I can find the endpoint there by plugging 3 into this equation, and I found that it's this point right here. I did not want to add those fractions together, so I just left it as 20 27ths plus 27/5. Then you can calculate the slope, again, by plugging in 3 for x and this horrible number for y. and I've got a really nasty slope here. For my next line segment, it looks like this. And you get the idea here. I can then find that endpoint and just keep doing this all day long. This is what the actual solution looks like. Let me graph this for you. It's in green. And you see that it starts off as a pretty good... Actually, no. It doesn't even go through that point, does it? So that's a bit of a bummer. Maybe that's not exactly the solution. Anyways, this solution here very closely approximates what's happening with the actual solution, which is meant to be the green curve. You see, we start getting steering away from it a little bit there because these lengths are a little bit too long. So if I made each interval like a half a unit or 1/10 of a unit or something, I would get a better approximation. Okay, cool. I hope this makes sense. We will be playing more of this in class, and I'll see you soon.